Okay, we have here another limit in which we have to resist the strong temptation to say the tangent of x is equivalent to x when x goes to 0, which is actually the limit we want to calculate. And also the sine of x is equivalent to x when x goes to 0. So you have here x minus x, and that is 0, so this limit would be 0. We have to resist this temptation because this result is wrong, okay? Actually, this is exactly what the problem, where the problem resides. When you have two terms like this, which are canceling each other, so subtracting, right? And if you do this, and this leading term, which is what this means, right? This is the leading terms when x goes to 0, cancels out because it's the same here and here. All that you are neglecting in this, in doing this approximation, right, is precisely what decides what the limit is going to be. So this, if you do this and substitute, you get a wrong result, right? So you shouldn't do this, okay? So what do we do then? Well, actually, in this case, it's easy because the tangent of x is simply the sine of x divided by cosine of x. So if you have the tangent minus the sine, you do have this. And as you can see, the sine is a common factor of both terms. So you have the sine, which multiplies 1 over cosine minus 1. And reducing this to a common fraction, where you have is the sine of x times 1 minus cosine of x divided by a cosine of x, or if you prefer, the sine divided by a cosine. This is the tangent. Well, it doesn't matter. We can keep it like this, right? So we substitute this here, and then we have the limit when x goes to 0 of the sine of x, 1 minus cosine of x, divided by the cosine of x and x cubed. Okay? Right. We can factor this limit in 3 pieces, right? The first one is the limit of 1 over cosine of x, this denominator here, right? Because this limit is straightforward. It's just substituting the cosine by 0, and then you get 1. Then you also have the limit when x goes to 0, and you take this factor sine here, and one of the x down here, and then you have sine of x divided by x. Another easy limit, because this limit is again 0. And finally, the third limit that you have to multiply by in order to recover this expression is 1 minus cosine. That's the last factor you have in the numerator. And in the denominator, you have already used the cosine 1x, so you're left with 2 more x. So as I said, this is 1. This one here is also 1. So the limit is equal to that, right? This is the limit when x goes to 0, 1 minus cosine x divided by x squared. But it turns out that 1 minus cosine x is equivalent to x squared divided by 2 when x goes to 0. So if we replace this here, now we can do that because this is just a quotient. What we have is the limit when x goes to 0, x squared divided by 2x squared. Now you cancel the x squared, and the limit is just 1/2. As you can see, this 1/2 is not the 0 that we had obtained had we done this incorrect argument here. And the reason is, as I told you, is precisely the cancellation of the leading terms what transfer the load of the limit, so to say. I mean, the terms that decide what the limit is to the neglected terms in this expansion, right? And you can see here is a combination of this x squared in the denominator with something that is equivalent to x squared, but decides what is the actual limit. So the limit that we want to calculate, the limit of this expression, is just 1/2.